Log on, tune in, find out. Another good idea from Cambridge.
Manuel Kendas. It's my very unusual for me task to introduce a talk entitled Some Applications and Hardware Implementation.
All right. I would like to thank everybody for staying all week. It's still a lovely day in Cambridge. Yesterday we were so lucky to discuss mathematics. Today we're going to discuss mathematics a whole lot less. But what we're going to see how mathematics may percolate down to applications. And of course I could be a journalist and be extremely dramatic and say it's life-saving, but I will refrain from saying such things. Today we're going to see applications of compressed sensing and the kind of hardware that people develop at the moment. There are many research groups worldwide trying to capitalize on these ideas and introduce some novel acquisition devices. I will show you some efforts in three areas. The first is in radio frequency acquisition, and we're going to talk about analog to digital conversion. Then I'm going to show you some efforts in optics, cameras, microscopes, things like this. And then finally, the example that is probably most well known, which is in MR. Okay, but these are the LMS lectures. And I thought, how can I speak 1 hour? How can I speak 1 hour without not showing a little bit of math? So I thought that there was this kind of Golden-Thompson inequality that generated quite a bit of interest. So I thought, I'll show you how it's done and what you can do with it. It's going to take 5 minutes, so if you're not interested in math, you can check your email and otherwise. Okay, so why do we like the Golden-Thompson inequality? Because it makes a lot of things very easy. One of the things it makes easy is this Alswede-Winter theorem that is trying to develop a large deviation about sums of random matrices. So we have a sum Sn, which is a sum of independent random matrices. So these are random matrices. The goal is, of course, to bound the spectral norm of Sn. Of course, if these were one-by-one matrices, we would know how to do this very well. We would calculate a moment generating function. And that's the idea of Alswede-Winters, is we're going to calculate a generating function. And so we just calculate the expected value of t times the trace of this sum. And if we can control this, we will have a large deviation bound. Okay, but Sn is, of course, the expected value of the exponential of the trace of Sn minus 1 plus xn. Okay, and that's where this magical formula comes in, which is that I can say that the expected value of well, maybe I'll put the trace outside to make things simple. So I'm going to put the trace outside. Of course, that's the same quantity. And so the magic of Golden-Thompson is to say that this is less than the expected value of the trace of t times Sn times t times xn. That's Golden-Thompson, says that the trace of e of a plus b is less than the trace of e at the power a times e at the power b. Of course, if these matrices were commuting, that would be obvious, but they are not, and it is not obvious. Okay? And then we say that for matrices a and b, because it's semi-definite, the trace of ab is always less than the trace of A times the norm of B. Okay, and so I can further bound this by the expected value of the trace of the first term. But now Sn minus 1 and Xn are independent, so okay, and I've got everything I need. Then we're back in the scalar case essentially. And so the proof of the large deviation bound continues just like if we had scalar. Of course, we're going to apply the same trick. This is going to percolate down, and therefore we're going to have a very good control of the expected value of the of the expected value of the moment generating function of the trace. Okay. Do I write clearly enough? Okay. So I said in my lecture on Wednesday that the whole thing is over here. This is where all the combinatorics is hiding. And there's a very elegant proof of Golden-Thompson. So I'm going to state Golden-Thompson, and I'm just going to justify it very quickly. So Golden-Thompson says that for any A and B, let's take them symmetric. Of course, they could be Hermitian as well. But the trace of and once you know this, I don't know how you cannot think of large deviations for matrix valued random variable. Okay, all right. So I'm going to provide you with a short argument. So we're going to see a very short proof of this fact, and we're going to use only one piece of technology, which is a Lie product formula. There are probably several proofs of this fact. I'm going to try to present the simplest I know, and that uses this fact, which is that the exponential of A plus B is a limit it goes to 0 of that's what I'm going to try to use. Okay, so I'm going to use this thing, and I think as we see, we're going to only need this. And now I'm going to prove Golden-Thompson, and for this, okay, we're going to write x to be exponential A over a large dyadic integer, so 2 to the k, and we're going to do the same for B. And now I claim that because of this nice Lie product formula, I just really need to show, so it's sufficient to show that the trace of xy at the power 2 to the k is less than the trace of x 2 to the k y 2 to the k. Can you see, can everybody see this? Or I'm behind the screen? I'm behind the screen. Okay, so I'll write on the other side. So the trace of xy at the power 2 to the k, if I could show that it's less than the trace of x at the power 2 to the k times y at the power 2 to the k, I'm done because of the Lie product formula. So what we need to show is that trace of xy at the power 2 to the k is less than trace and if I can show this, I'm completely done because of the Lie product formula, because when k goes to infinity, by definition, this is going to go to this, and the right-hand side is already what I want. So, all right, so I just need to show this. Okay, so it's sufficient to show this. And the last thing that we're going to use is something that I'm sure everybody knows, that the trace of a matrix Z is less than the sum of its singular values. Okay, so the trace of Z is less than the nuclear norm, which we've discussed extensively yesterday, which is nothing else but the trace of Z star Z at the power 100. All right, and by analogy, I can raise it at some power. The trace of Zm will be less or equal to the trace of Z star Z at the power m over 2. Okay, and so now once we've got these two facts, the fact that we know that the nuclear norm upper bound, the trace, and we know the Lie product formula, the proof of Gordon-Thompson is a few lines. I mean, 3, I think. And so what are those 3 lines? So I'm going to start with the trace, the left-hand side, the trace of x, y at the power 2 to the k. Okay, and that's going to be less by what you see on the right-hand side of the room than the trace of, well, if I call z this guy z, it's going to be less than the trace of z star z at the power 1m over 2, so it's going to be 2 to the k over 2, so it's going to be 2 to the k minus 1 of z star z. But what is z star z? It's going to be xy star xy at the power 2 to the k minus 1. Okay. But now x and y are symmetric, so this is going to simplify because x and y are symmetric, so they are self-adjoint, and therefore I can rewrite this as this because they're symmetric. That's right. Okay, so Gordon-Thompson only holds for symmetric matrices. Okay, so we've got this. And then I'm going to use the fact that the trace of UV is the trace of VU, so I'm going to commute this. I'm going to say it's the same as this. Okay. But now we're done because I can repeat. Because now I just repeat and I just say, let's play the same game again. And so then, of course, this power each time is reduced by a factor 2. Each time this is going to be increased by a factor 2. And so I'm going to be able to show by exactly the same argument that the trace of x squared y squared at the power 2 to the k minus 1 is less than the trace of x4 y4 at the power 2 to the k minus 2. And I repeat this k times, and I have Gordon-Thompson. Okay, which is, in my view, a pretty deep inequality, but if you know Horn and Johnson, can be taught at a beginning graduate level. All right. Okay, and that's again where all the combinatorics is hiding. And actually, with this, you can recover. Of course, you don't get the constants right, but you get lots of results from random matrix theory by just applying these things. By the way, an interesting thing about this is that you see how much it depends on the fact that I have only 2 matrices and not 3. Because otherwise I would have x, y, z, and things would be horribly impossible. And in fact, Gordon-Thompson is not true for exponential of a plus b plus c. It is not less than the trace of EA times the EB times EC. It's only true for 2. All right, so now we're done with the mathematical interlude. So I fulfilled my contract. All right. Okay, so we're going to talk about application. The first application we're discussing, but before we move, any questions about this? About Gordon-Thompson? No. Okay. All right, so let's talk about applications of compressed sensing. All right, so we're going to talk about analog to digital conversion first. And well, everything we build pretty much, every circuit, cameras, everything we build is based on this Nyquist-Shannon foundation, which has been discussed yesterday, which says that if I want to acquire a signal that is band limited, I need to sample at twice the bandwidth. So for example, if I want to acquire a signal in a gigahertz band, I need to sample at 2 gigahertz, which means that I need to take 2 billion samples per second. And what Shannon says is that if you take 2 billion samples per second, I can provide you with an interpolation formula that can recover the signal in between samples, of course. All right, and that's great. And that's what we've built building everything upon. The little problem with this, it's not a problem, it's just a fact of life, is that signals are wider and wider bands. So here what you're looking at is frequency allocation, frequency spectrum allocation in the United States. I think 300 gigahertz of bandwidth have been allocated, and that's very, very large. So the fact is that signals are wider and wider band, and in the business of digitizing signals, there is something like a Moore's law. And what the Moore's law says is if you can sample with a given accuracy a signal in a given frequency band, how long do you have to wait to put your hands on a similar device that would sample a signal at twice that frequency with roughly the same accuracy? And that's going to be about 8 to 10 years. So if you have a good product that samples at 200 megahertz, and you say, I want to have a good product that samples at 400 megahertz with the same effective number of bits, what you have to wait is about 8 to 10 years, which means that if we really want to acquire wide signals that can capture wideband signals, they are really decades away, and that is a bit of a problem. All right, so there was this program manager who designed a very innovative program and who encouraged us to apply to this program, and so we got funded about 5 years ago. His name is Dennis Healy, who realized that compressed sensing might offer a way out of this dead end. And so he pushed us, and me in particular, to kind of try to apply what I knew mathematically into effective hardware. Okay, and so I would like to dedicate this lecture to Dennis, who passed away 2 years ago. All right, of course, there's nothing wrong with Shannon. Shannon said that if you're interested in any band-limited signal, you need to sample at that rate, and that's a sharp theorem. There's nothing you can do about this. The thing is, are you about to see something like this or something like this? And not all band-limited signals are created equal. All right. And so it perhaps you think that as we think about signals that occupy larger and larger bandwidths, clearly their information rate has nothing to do with the total bandwidth. Okay, and so Shannon theory is not that relevant. All right, so what we've learned during this week is that, well, if somehow the information content of a signal is far less than the total bandwidth, then I should be able to sample way below the Nyquist rate without information loss. And whereas Shannon has a nice sync interpolation formula that we've seen yesterday, we do not have such a thing. What we have is we have convex optimization to interpolate the missing between the missing samples. Right? So just to remind you, suppose that for simplicity, we have a structured signal in the sense that I have perhaps a communication signal that occupies a very large bandwidth, but is spectrally sparse in the sense that in a given time window, when I look at its spectrum, most of the frequencies are not occupied, which is typical of lots of bandwidths in the way RF spectrum. Then what we've learned during these lectures is that if I were to sample this signal at random, non-uniformly in time, and if I were to make sure that somehow the density of points I get is 4 or 5 times the fraction of frequencies that are truly occupied, then this is a sampling scheme that has no information loss. All right, and so we're going to try to capitalize on this in trying to design systems that do things like this. So with the company and with many colleagues, it's a big joint effort. We actually spent the last 4 or 5 years building chips. And these chips will essentially implement ideas of compressed sensing at the circuit level. These are very tiny chips. For example, this chip, these are all to scale. I mean, there are things that I think the vertical distance that you see is about the The height of the first chip is about 1 millimeter. You can fit several in your cell phone. So we have built 3 chips, 2 in a process called indium phosphide, and 1 in a process called CMOS. And this chip, which is we call the non-uniform sampler, is essentially messing up the clock of a regular ADC. So this is not working anymore. Okay, is messing up the clock of a regular ADC so that it's actually sampled non-uniform. So the first chip is a very simple implementation in some sense. It's easier from an engineering point of view to manufacture. What it does, it samples but non-uniformly in time. And what it's good at recovering sparse signals, and when sparsity is expressed in the frequency domain, signals with sparse spectra. The second two, the last two, are more complicated, and they really try to implement the full idea of compressed sensing, and they're going to really take some kind of random mixing. All right, so we have 2 versions of it. We have one in CMOS and one is indium phosphide, and I will explain a bit what the architecture is doing at a very, very, very high level. All right, so we've got a radio frequency wave that is coming in. And of course, as I said, I cannot sample at the Nyquist rate. And our prototype is actually designing to cover 2.5 gigahertz worth of bandwidth. So the Nyquist rate is 5 gigahertz. You have to realize what that means. It means the Nyquist rate is 5 billion samples per second. Right? It's 1 DVD worth of data every second. So we cannot sample at the Nyquist rate, but what we can do is we can change the polarity of the incoming radio frequency wave at the Nyquist rate. And so we're going to apply this basic idea of compressed sensing where the signal comes in, it's amplified, of course, there's a nonlinear amplifier somewhere, then it's split into several channels, and if you look at what a channel does, it really does the most basic thing you could think of. It's multiplying the signal by a random sequence of plus and minus ones on the fly. So this is called a digital mixer. Then the signal is integrated, and then we're now going to sample the product of the multiplication followed by integration at a very slow rate, at 50 megahertz. All right, so if we go back to what this lectures were about, what this is doing is essentially something like this, where I have a function of time that is multiplied by a random sequence of plus and minus 1. Integrated means that I take the inner product between a function of time and a random sequence of plus and minus 1s. All right, so engineers, think about this as you spreading the spectrum. All right, so if a sinusoid that comes in had a very sharp spectrum, this will completely spread it out so that you can actually now effectively sample. Okay, so the Nyquist rate in our apparatus, it's 5 gigahertz because we're at 2.5 gigahertz worth of bandwidth. This is joined with Azita Imami, Yuhan Yu, and Stephen Becker, my grad student from Caltech. So Yuhan and Azita are circuit designers, and Stephen Becker is an applied mathematician. All right, and it's fair to say that these people, that of all the 4 of us, I did the least work. All right, so this architecture, what it does, it has 8 channels. Each is sampling at 50 megahertz, so the total sampling rate is 40 megahertz. We're undersampling Shannon by a factor 12.5. And so we're committing a big crime, of course, and when we went to work with this company for 2 years, they really did not want to talk to us because, Shannon is the thing you don't want to challenge at all. Okay. All right, but nevertheless, we actually build chips that do this. This is our version 2 of this kind of random modulation, pre-integration, random modulation. So you randomly modulate the signal by this random sequence of plus minus 1, and you integrate. And so it's a chip which is tiny. As I said, this is about 2 millimeter by 2 millimeter. It has a small power consumption of about 830 milliwatts. It covers 2.5 gigahertz of bandwidth. It has a dynamic range of 50 dB, and its sampling rate, as I just mentioned, of about 400 megasamples per second. Now, I'm not going to talk about computational issues. At the end of the last lectures, I talked about, yes, so you're going to have to recover, you're going to have to solve a problem with 5 billion unknowns every second. That's a bit daunting. For most applications of interest, you actually don't care about recovering the full signal. You want to extract things about the signal of interest, which reduces computational workload. But one big component in this project is actually how do you carry these data-intensive calculations, and this we do on GPU arrays. Okay, all right, so that's the chip, that's how it looks like. And the chips is producing data. I'm not showing you real data yet. They should be published this summer, and okay, so I'm not in position to show you complete real data yet. What I can show you are full-scale system simulation using SPICE, which essentially models everything in the chip. And what we see is that you're gonna has an input signal. So you have two plots of the input signal. You have a plot in the time domain. So what we see is we have two functions in time that overlap, but these two functions are pulses, and they are pulses at very, very different frequencies. So they are functions. Maybe I'll write down a basic formula. They are functions that look like this: g of t minus t naught over a scale exponential I omega t. So they have a frequency carrier omega, they have a duration sigma, and they have a time of arrival t naught. And so if we look at these two pulses in the frequency domain, they are very far apart. So one is at 100 megahertz, and the other one is at 2.4 gigahertz. And of course, our chip is dramatically undersampling Nyquist. And in blue, we see the original spectrum of the signal. This is a log scale, by the way. It's a power frequency scale. It's a dB scale. And what we see in red, you see our recovery from full-scale system simulations with all kinds of non-idealities. And so you see that you do very well. You actually recover these two pulses very, very well. The noise floor is on a dB scale. So, you have almost 4 orders of magnitude between the peak and the noise floor. Right. This is a recovery in the time domain using some of the algorithms we've discussed. To connect this with lecture number 3, we use overcomplete representations to recover things like this because we don't have good orthobases to express sparsity for things like this. And so that's why the theory that I presented on Tuesday is useful. What you're seeing now the recovery once we take out the carrier frequency, because if I let this thing oscillate, you would see nothing. So after demodulation, you see that you recover the signal very, very well. In fact, the error that you make in estimating the frequencies there's almost no error whatsoever. Okay, so it seems that we can surveil a very large bandwidth even though we're undersampling Nyquist by a huge amount. Okay, so this is another experiment of the same kind, and it seems to work for many, many pulses. They may overlap in time, they may overlap in frequency. It doesn't really matter because, again, what we are applying is this principle that what we're seeing is not white noise. We know in which basis these things are sparse, and so the system should work, and indeed it works. All right. So now when you work on things like this, you're going to have to get your hands a bit dirty because it is absolutely not true that the theory directly applies. You're going to have to deal with lots of issues. To me, the top issue is a calibration issue. And we spend, well, when we're now designing chips, we spend all our life trying to understand what they do. And one thing is to say that, and I think there was a question about this, one thing is to say that the chip does this, that this is essentially the sensing waveform, but that's not what it does because I cannot control a mixer with infinite precision. So it does not do this. So what does it do? And so we have to understand, of course, compressed sensing is completely robust. You know, it doesn't have to be a random sequence of plus and minus. It can be pretty much anything as long as it's incoherent. But I need to know what it is so that I can invert the matrix. And the thing with this thing is that it's not easy to actually understand what it does. And so calibrating these things takes a very, very long time. And that's why progress in electronics is not as fast as progress in mathematics. Of course, there are algorithmic issues about how should you express sparsity, which algorithm should you choose, how do you choose the various parameters. Well, these are things you need to worry about. Other things you need to worry about is that, of course, you have a non-ideal system. And I want to connect this to the lecture on noise, which is that if compressed sensing was extremely sensitive to either the matrix, precise knowledge of the matrix, or that the fact that information is in the fifth digits of the measurement, you would be in big trouble. But of course it's not, and that's why these systems work. But in practice, we have to deal with clock jitter, that we cannot time things as precisely as we would want. In fact, there's a trade-off between clock jitter and the energy consumption, because there's Heisenberg somewhere that says that delta T, delta E needs to be greater than something. Right? And that at the clock rate that we're looking at, Heisenberg starts to show up. Because when delta T is 10 to the minus 12, 10 to the minus 15, it gets significant. We have to deal with nonlinearities associated with these amplifiers. We have to deal with thermal noise, the fact that integrators are not what they should be, and things like this. And so just to show you, one of the things that might go wrong in the compressed sensing model is in reality, when the signal is large, you're not sensing AX, because there's an amplification step. And so what you're going to sense is not AX, what you're going to sense is not X, but rather a nonlinear function of X, like a polynomial. Right, and that is a bit of bad news, because if X were sparse, P of X may not be sparse at all, because you're going to create harmonics all over the place. And so if you had sparse signal in the frequency domain, then P of X will not be sparse, because you're going to create harmonics. And so that's not good. And so this may destroy sparsity. You're going to need to correct for these things, and that's why there's a lot of work, real work, that needs to go into these things. Right, so for example, if I were to look at a similar experiment where I do not correct for nonlinearities, and I do my reconstruction a bit naively, I'm going to get a reconstruction that has what we call a compression gain, or gain compression. That the reconstruction is not as good as I would want it to be, right? Because the model is wrong. The model is not that I'm sensing AX, I'm sensing A of P of X. And when this coefficient is not negligible, and when X is large, we have trouble. Okay. But, we're designing methods to correct for such things so that, we try to minimize these effects as much as we can. And so after correction, we get good recoveries of these things. All right, but that's the kind of things that you need to take care of when you really try to apply the theory in practice. Lots of things will go wrong everywhere, and you have to work to actually to make them work in real life. All right, so these chips, as I've said, have been manufactured. They're producing data. You see the 3 chips we've seen at the beginning. They're on the test board. And so we collect data about these chips. We try to understand them and do all kinds of stuff with them. All right. So things is going well. I mean, it's been a very long. We've worked on this since almost the first papers on the subject. We started 2005 to work on this. Still, we don't have papers to show because it takes a very, very long time. All right, but in the lab, the data we get show that the chips behave as the simulations you've seen. There's not much difference. I want to say that we're not the only ones to work in this area. There are other groups, and I just mentioned a few, but there are many others who essentially also try to design analog to digital converters at some subsample Nyquist. My colleague Yonina Eldar at the Technion has an implementation with discrete components. L3 and the University of Wisconsin are also working on this. People at RISE, lots of people are working on this. Academia and industry, right? L3 is a company. There are people in academia and industry are trying to do essentially things like what you're seeing here. Okay, so that was my first stop, analog to digital conversion. And the second application I want to mention are optical systems. All right, so I guess the most well-known piece of hardware associated with compressed sensing is the so-called single pixel camera, where there's a race nowadays to go towards more and more pixel, and these people go the other way. They try to say, can I actually have only a 1 pixel in a camera? And the idea is like maybe the epitome of compressed sensing, because it's really what we've seen in this lecture. What you've got is you've got an image, and if you had a standard camera, this image would go through. I mean, we have the scene that we would like to take a picture of. Then light would go through a lens and then onto a CCD array, for example, the pixels you have in your camera. In this camera, you go through a lens, of course, to focus the light, as usual. I mean, we're not going to eliminate completely optics. No, of course, you go still through a lens, but now instead of hitting a 20 megapixel array, you hit what is called a digital micromirror array. These are tiny mirrors. Right. I hope I have a picture somewhere. Yes. Right. So this is the same picture. So these are tiny mirrors. Right. So you imagine that you have a very small surface with on it lots of tiny mirrors. And these tiny mirrors, they can have two orientations. You see one orientation and you see another one right next to it. All right. If the orientation is, let's say, this way, pointing towards you, then the light is going to be schematically represented with a white square here, and the light would be reflected to a lens and then to a photodetector. If the orientation is in the different way, schematically I'm going to represent this as a black pixel, and so the light will be reflected elsewhere. And what is this device doing, essentially? It selects a random grouping of pixels, and it just sums the photons hitting those pixels. Right? So it's a compressed sensing acquisition mechanism, because what it does, it essentially measures a random sums of pixel intensities at each measurement. All right, so now you program the thing to make patterns like this, for example, and then you put everything onto a photodetector. So this actually captures the sum of intensities at various pixels. Then of course this is changing with time. So now these guys, they have frequencies of operation at 30 kilohertz. Right, so you can make 30,000 random projections in a second. You put everything on a photodetector, you digitize the output, and what compressed sensing theory says is that you're holding your signal in compressed form. Okay. Why is this interesting? I mean, are we going to buy things like this? I don't think so. But because, well, the reason is because I think we're not going to buy things like this is because, at least for taking vacation pictures, is that digital cameras are cheap enough. But if we were interested in imaging in a different domain, like for example, let's say we want to look at an image at different wavelengths, for example, in the near infrared, then what used to be a very cheap camera becomes a very expensive camera, because the detectors, the chemistry is not working well anymore. That is, you can't use CMOS or silicon to actually detect these incoming photons. They don't have the right energy for the right chemistry to happen, so you're going to have to use other types of detectors, which are very, very expensive. And if you want to buy a high resolution camera that works in the near infrared, what is in the visible light costs $200 will cost you tens of thousands of dollars in your IR. But because you have only a single photodetector, you really need one sensor and not 20 million or 10 million. And so this could be very interesting to actually do infrared imaging at a cheap cost. And so I think that there are companies that are starting to take this idea and build CS IR cameras. We've seen papers producing images in infrared using these techniques. And so there are some people who think that that might be a very good thing. Now, of course, why do you limit yourself to a visible wavelengths? You could actually have a spectrometer because, of course, your photon detector may have more than one mode. Your detector might see things in various bands, and so you could have, because you have only one of them, you could actually do multispectral imaging at a cheap price, and so you could actually image in various color bands and get really resolution that lots of biologists who do biological tissue imagings and things like this would care a lot about. Okay, so there's a lot of enthusiasm in the community for things of this kind, of being able to take these ideas and essentially build optical devices that would collect lots of data, of interesting data at a cheap price. All right, so many people work on this. David Brady at Duke, Bill Freeman at MIT, Kelvin Wagner at Colorado, Rafi Kochman at Yale, Paul Hassler at Georgia Tech. I'm forgetting lots of people, but really the number of groups building kind of compressed sensing imagers is very wide, just to show you that the RISE people are not the same, are not alone. So this shows well on my computer, it doesn't show well here. People at Georgia Tech are also building cameras that take random projections and can produce high resolution images. So here it's a group of Paul Hassler. All right. Personally, I have an interest in microscopy and confocal microscopy, and so I started a collaboration about 2 years ago, a bit more than 2 years, with colleagues trying to kind of use compressed sensing techniques to address issues in microscopy, and I'll discuss what these issues are. So we're going to talk about confocal microscopy. A confocal microscope is a piece of equipment that looks like this. And microscopy works by fluorescence microscopy works, well, I'm sure everybody knows what this is, but okay, so what you're doing is you have a sample here, and what you're going to do is you're going to shine light on your sample. You're going to excite molecules here. They're going to absorb the energy, and then they're going to re-emit this energy, and the re-emitted energy is what you're interested in imaging. That's how we make images, by collecting the emitted light. Okay, so that's fluorescence microscopy, and people produce images like this, which are very important to image, for example, biological tissues, cells, things like this. All right. Now, what is the problem with microscopy is that when you do fluorescence imaging, let's say that you want to image at a given depth. And so you're going to excite the molecules here by sending light over here. But as you do this, of course, you're going to, since you need to shine light, you need to use your laser. You're going to excite everything what's above and everything below. And so all the molecules in your sample are going to be excited. They're going to all emit light. You're going to collect the light, and so you're not going to be able to perform what people call optical sectioning, because all the light which is out of focus will come back as well. Okay, because there's no way I can have photons hitting these things without going through here or continuing and okay. So you're going to have out of focus light, which is very problematic, which means that everything will be blurred. But there's a very cool idea in this field, which is this idea of pinhole microscopy, which is, could I actually eliminate out of focus light? That is, all these molecules that are emitting here out of focus can actually block their light. And yes, we can, and we can by putting a pinhole in the system somewhere, which is this thing that you see here. And now if I were to actually illuminate this sample, then I'm going to have three bands here for simplicity. In the schematic diagram, I have green, red, and blue. And what I can put my pinhole in such a way that the light emitted in the green or in the blue is not going through the pinhole, and only the light emitted in the red at the red depth is actually going through the pinhole. And so I can perform what is called optical sectioning with pinhole microscopy, and that's good. But as you can see, for this to work, I need to actually only illuminate a focal point. I cannot do wide field illumination anymore. So people can get high resolution images, but the price to pay for it is that you have to do point excitation and point detection, that now you're going to have to use raster scanning to actually go and raster scan through the entire image and image one point at a time. And it takes forever to make images. And so the idea is, well, we just get better excitation patterns. Can we do some kind of structured illumination, a pattern excitation, put everything back onto the single detector, but instead of illuminating just one point, we could illuminate several points simultaneously. Okay, and so we've built an apparatus that is essentially using the same DMD technology to actually create pattern excitations that will essentially illuminate the sample at carefully chosen points. And then of course we put everything in a single photodetector, so we get the sum of these intensities, but then we change the pattern, and then we're going to use this L1 magic to try to unravel individual contributions. Okay, so all right, so this is our experimental setup. Before I say, this is joint work with Jérôme Bobin, who used to be my postdoc at Stanford, now is in France. Maxime Dahan, which is at l'École Normale in Paris, and Vincent Stutter, who is at the University of Bordeaux. And just like in the previous project, if there's somebody who does the least, that's me. Okay. All right, so we have our setup like this, where we do excitations with our laser. All right. Okay, so it goes through a lens. The lens focuses on the digital micromirror array. This creates patterns, which you see here, that are essentially then illuminating your sample, goes through the objective of the microscope, light is fluorescing back and gets back to the photon detector. Okay. All right. These digital micromirror arrays is what you have in this projector. That's what is used to actually project light onto the screen. They're made by Texas Instruments. So we can program them to kind of make any pattern we like. In real life, we're never going to make random patterns, because for the reason that I explained yesterday, that I cannot deal with matrices that I need to store implicitly. I'm going to make structured patterns, looks like Hadamard transforms, so that I don't need to store them, I have fast algorithms and all that stuff. Okay, so we make Hadamard patterns, right? Think about them as, square sinusoids. That looks like this, and that's what we use. Okay, so now I'm going to show you a little bit of something funny, where um, we're gonna play a movie in the computer, right? With the computer. The computer is going to drive the digital micromirror array. It's going to project the movie onto the DMD. The DMD is going to project the movie onto the sample. The sample is going to be fluorescing, all right? And then we're going to see what we get here. So does this is clear what we're doing? Maybe not, huh? No, it's not clear at all. Okay, so we're going to play a movie. All right? We're going to play a movie. So maybe I'll show you the movie. But what I'm going to tell you is okay, so I'll show you a movie. Okay? All right. This movie is actually the recording of what's happening on a tiny plate inside the microscope here. Right? So how does this work? What I do is I have a movie, and so we know how to project a movie onto a screen. Right? We know how to do this. And how do we project a movie onto a screen with this DMD array? Micromirror array. That's what it does. I don't know if some of you watch, I use sometimes this device to watch movies at home, right? That's exactly what happens, right? So we create the movie. The movie is actually turning the mirrors of this DMD arrays. And so if we had just an optical system, it would be just something like this, and we would see Homer's movie, the Simpsons movie on the board. But actually, this movie is actually now going through a bunch of lengths, and is actually illuminating in this movie pattern now a fluorescing sample, which in our case is just, we took a tiny plate, we put we have this stabilo boss, it's boom. Now, so this is a pattern excitation with which pattern? Well, what you just see. Oops. Why is this now? Okay, so this is playing in reverse. Right, so now this guy is fluorescing, and it's fluorescing the movie, of course. All right, and what you're seeing is this movie, but that is fluorescing over here. Okay, it's on the tiny thing, right? So. So it's a movie that is actually playing on a thin slice of a fluorescent thing that is over here. Okay, so now how do I move forward? I have no idea. Okay, all right, so that's kind of the idea of this setup. These images you can't see. So we do beads imaging, which is what people care about. But we can't see really. We do cell imaging, so there's contrast here, but there's not really contrast. So we do biological tissue imaging, and what we can demonstrate is with a heavy dose of undersampling, there's not much difference between the recovery of those biological images. All right, so this is what we're doing at the moment. Okay, you can't see these images. I don't know why. Of course, they're faint because the signal-to-noise ratio is not high, but we can undersample images, and when I look at them on the computer, they look fine, but here they don't really look fine. And we can actually build hyperspectral imagers on top of it, just like what people at Rice suggested, so that we can look at tissues in various color bands, and that's what we're doing as well. Okay. All right, so we have a hyperspectral setup so that we can look at tissues at various wavelengths. And what we're going to do in the future, so right now we can do only 2D imaging. And what we would like to do in the future is really to do deep tissue imaging, which is this thing. Right? And so you're going to ask me, well, how can I focus light on this slice and not everywhere else? Well, we're using 2-photon microscopy to do things like this. And so the real goal for us is not really so much what you've seen. This is just to get familiar with calibration, warming up, all these things. But it's really after going to 3D deep tissue imaging, and that's going to be much more difficult. All right, any questions about this? No. All right, so we see that people build cameras, people build microscope, people build all kinds of things. All right, the last things I wanted to mention is fast magnetic resonance imaging. So you're going to see black slides from now on. They are not mine. They are slides that were given to me by Michael Lustish and John Pauly. All right, so this is the MR, things that we've been discussing a lot during these lectures. MR is a wonderful imaging technology. You can see tissues with MR. It operates by measuring the Fourier transform of proton density, and people like it a lot because you can see stuff with MR that you cannot see with CT. It's also less, I believe it's less toxic because you don't use radiation. All right. As we've explained many times during these lectures, and people have done a better job than me to explain this, MR data collection is very slow because of these relaxation times of spins. And if we could do faster imaging, then we could decrease scan time, decrease image artifacts which are caused by motion and blur. We could increase spatial and temporal resolutions because now the reason we cannot really get high resolution MR scan is because it takes a long time, and so you're going to have motion. We could increase coverage, we could do new applications, we could actually do movies and so on. And of course, the only way really we have to do faster imaging, or a possible solution, is by reducing the data rate that is being sampled. Okay. The problem with MR is, for example, the true need for speed, and that's a beautiful argument made by Michael Lustish and others, is that it has the fact that we cannot take fast scans is a bit of a problem when you want to detect disease in children. Because children cannot stay still, they cannot hold their breath to actually for a long time. And so whenever you try to use MR on uncooperative children, it's very difficult because everything gets blurred and it's impossible to come with a diagnostic. Okay, so here you've got a pelvic scan after a patient becomes restless. This is a good scan. This, you can say something about this. You can see dots, things that are of interest to doctors. But if you become restless, then you cannot diagnose things. All right. And so for this reason, and this reason alone, on top of all these reasons, it would be a very good idea to be able to increase the scan rate, because all of a sudden maybe we could use MR for pediatrics. Okay. The current solution to actually use MR is to inject a heavy dose of anesthesia in children, and that's very dangerous, and I'll say a few words about this in a minute. Try to use different imaging modality, but you may not see what you want with different imaging modality, and also they might be more toxic, such as computed tomography. All right, so imaging, we know that you collect Fourier samples. Faster imaging means undersample in the Fourier domain drastically, and of course, this is what we've seen. Maybe I don't need to say. You undersample the Fourier transform, you use a standard reconstruction, that's terrible, but if you use the kind of stuff you've seen, then there's no error, at least on the good old Logan-Shep phantom. All right, and so that's what kind of radiologists are interested in, the fact that you can dramatically undersample the Fourier transform. You can throw away 84% of the Fourier sample, and on images like this, you still do not have any kind of loss. And so for them, it's interesting because it means that a scan that takes 2 minutes could take 20 seconds. Okay, so there is a lot of work in the MR world about trying to use these ideas to come up with better scanning techniques, faster scans, and so on. I'm going to discuss the work of Mickey Lustig quite a bit, but there are many other works. One of the early work is also by Josh Trashko, Manduka, and Borish from the Mayo Clinic. And so here is a scan that you get with fully sampled data. This is a scan with when you undersample, but you use a classical reconstruction algorithm. I don't think you can see very well, but things are very blurred. And here is a scan with 6 times undersampled data. And I cannot see lots of difference between this guy and this guy, but I'm not a doctor, so it doesn't mean much. These people, Josh and his colleagues, are very enthusiastic about all of this. They actually developed this methodology to actually build up 3D fast scanning techniques. What's good about 3D and 4D and 5D and all these things is that sparsity keeps on increasing. That is, 1D signals are so sparse, 2D signals become sparser, 3D signals are kind of very sparse, 4D signals, it's insane how sparse they are, 5Ds and so on. Okay, so in 3D, they have actually, I think, from what Josh told me once, but don't quote me on this, I think this is prototype on Siemens scans at the moment, where they use their technology to actually reduce the scan time of a scan. And here is a picture with a full scan, here's a picture with a 6 times undersample, so 6 times faster, and it looks good. And it's really 3D, so here's a different view of the skull, right, and then the recovery. Okay, of course these algorithms are computer intensive, but we live in an era where we're going to move into cloud computing, and so you're just going to let the cloud do its thing. And a scanner is so expensive compared to 5 minutes of computing time on a supercomputer that the computational cost here is really not an issue. Okay, so let's go back to Mickey Lustig. Lustig has been a very big proponent of compressed sensing for MR. Here is a conventional image produced by a conventional scan. This is his method using L1-like ideas, and he calls it spirit, and he claims that, well, I'm sure they are better than the things this compares it to. And so this kind of L1 magic seems to be of use in MR. But let me come back to this idea of pediatric MR, because a year ago, I think there was a dramatic story published in Wired magazine about compressed sensing, and it was about an experiment, not an experiment, a real-life situation that happened at Stanford Hospital. So Mickey Lustig is actually testing some of the ideas at Stanford Hospital, and what happened was this: is a boy who was 2 years old, and he had received a portion of a liver about 10 months earlier, but the liver was functioning well at the beginning, but it started to fail, and there was something terribly wrong with it. And his life, what that's the article writes, was okay. And to know what was wrong, you needed to take a very high resolution scan, which, at least given the technologies they've got, meant 2 minutes of complete. You have to stop respiration for 2 minutes. And but then Mickey came along and said, but maybe I can take a quick scan using these ideas, and I can reduce scan time, and maybe I can use my reconstruction algorithm to produce a super resolved image from far fewer samples using these techniques of compressed sensing. And so they did this. They run a scan for 40 seconds instead of 2 minutes. That's a factor 3. Reduction, what meant is that the dose of anesthetics they had to inject was far less than what you need to inject to stop the heart for 2 minutes. The child suffered no appreciable oxygen loss. The image was so crisp that the doctor saw immediately what was wrong with this guy, and then everything went well. All right, so what I want to say through this story, which I've read in the papers, and then I met one of the guy. I met this guy who did this thing. His name is Vasana Walla. Is that these techniques are not used clinically yet, but they're used to help diagnostics at the moment. Okay, so they are used to reduce the scan time for children. So here's the scanner. So they put little monkeys so that children stay quiet. And then they do their magic. They undersample and then they reconstruct using this L1 spirit. L1 spirit, it's here. And then they produce good images with L1 spirit compared to what's conventionally available, maybe with the same exposure time or the same scan time, and so they get sharper images which they can use for medical diagnostics. Okay, so their papers are full of convincing imagery that shows that what you can can get with these techniques is superior to what you can get with perhaps conventional approaches. And so, you know, this is what you can get, this is what you can get, and here you see like areas that are of special interest to people, and here it's not clear what's going on, but here it's clearer, and the same here, and compared to here, and things like that. Okay. I think one of the things that is very interesting in what Michael has done is that, if I understand correctly, you know, PSNR may not tell you the whole story, because what matters is what a doctor can actually diagnose from an image. And so I think that they've run psychophysical experiments where they were subjecting doctors to two reconstructions, classical reconstructions and this L1 spirit reconstruction, and then they were able to test various methods using doctor assessments, and it seemed that their methods are quite pleasing from the statistics they report. And so it's not only that they do well in a mean squared error sense or in a PSNR sense, but they do well in what people want to see. Okay. All right, so that was my slide on my slides on, and Mickey's slides on MR, and so there's a lot of work. Again, it's exciting. You get lots of research. I think much more research is about to happen. Also, all these computational issues and how you reconstruct these things are very, very interesting. Compressed sensing is on board of satellites at the moment, because in a way you can use compressed sensing as a cheap compression scheme, and that's what this satellite does. It uses compressed sensing as a cheap compression scheme. And this goes back to what I think I discussed earlier in these lectures, which is that, you know, because a satellite wants to send to Earth a few bits, because communications, it's so far away that communication power is so expensive, you want to send as few bits as possible. Then if you have cameras on board of the satellite which take images, you need to compress them down to not send many times the same information. And how do you do this? Well, you need to run CPUs to do the compression. And that's energy intensive. That's why cameras run out of batteries. But if you had a compressed sensing acquisition, then you don't need to compress. It's already compressed. And so you can perhaps save energy, which of course, as you can imagine, where is a satellite orbiting Jupiter is going to get its power. All right. So in summary, to summarize this last lecture, we talked about mathematical sensing. I think it's a sentence by Dennis Healy, which is the idea of bringing mathematics into the lens, into the sensor itself. I think we've seen already many prototypes of CS ideas. Time will tell whether they survive or not. They may not. We'll see what happens. It will depend on our ability to calibrate things, I believe, and we'll see whether we have the patience of doing it. But I think in any event, it's an exciting time because what we see whenever I look around me is I see lots of people building instruments, and they're always looking for opportunities to collaborate with mathematicians so that we can build better instruments, and so that mathematics does not come as an afterthought. You know, the good old days where you build your camera and then you ask a mathematician to do signal processing. And I think we have changed, and that's what's so great about the time we live in, where mathematicians can have an input in the way you design your camera in the first place. Right? And that's kind of what these ideas and compressed sensing are about, is to try to bring mathematics into the sensor itself. I think it creates wonderful opportunities for lots of us, and it's, as far as I can tell, a very exciting time. Thank you very much.
Are there any questions?
I have a question regarding the RMPI, the ADC that you presented. The power consumption of the unit is just the ADC itself, not the GPU computation needed to perform reconstruction.
In fact, most of the power consumption in the ADC, what's interesting about the power consumption, I showed you two figures of power consumption. There's a discrepancy between the two, and I'm surprised nobody...
one was
8.30 milliwatt, the other was 3 watts.
Yeah, exactly.
The reason is, when you look at the RMPR architecture, you can try to separate where the power consumption comes from. And the power consumption, 830 milliwatts, is everything here. It's amplification, modulation, integration, but not the ADC samplers themselves. In fact, most of the power consumption in the chip comes from the individual ADCs, not from all those random modulators. This is cheap in comparison.
But usually you use parallel branches to divide to achieve better sampling rate. In general, did you consider if there's any, let's say, golden ratio between implementing more parallel branches, because then you're adding additional ADC, for example?
Yeah, but then we need to sample at a lower rate, right? So, which is a good thing because then they become more accurate. There is less clock jitter. You have more effective number of bits and so on. That's true what you're saying. I mean, compressed sensing, the basic theory of compressed sensing says the more branches you have, the better, because you should be as parallel as possible. That's the theory of compressed sensing. In practice, putting a lot of these channels, so they are designed, you know, we have 8 channels. We have 8 pieces of the chip that do essentially the same thing. 1, 2, 3, 4, 5, 6, 7, 8. We could try to put more, but that's becoming tedious. We have crosstalks between these components. We found that 8 is a good number. And the reason we found that 8 is a good number is because we have target signals that we care about, pulses, for example, and in any given time window, we would like to have roughly 8 views of this pulse. And of course, if you could build more channels and sample at a lower rate, that would be better because you would be closer to these IID matrices we've been discussing all along. But we found that we got good results with 8. And of course, as a complexity, 16 is more complex, and we prefer not to go there at the moment.
You also never mentioned anything about quantization. I mean, because you mentioned many issues, clock jitter, thermal noise, but how about quantization itself? It doesn't matter if you have ADC with 4 bits resolution or rather 16-bit resolution.
Well, yeah, I mean, you want that your quantizer is not the limiting factor, right? Right now, the limiting factor in our system, we have fairly effective ADCs because we need high dynamic range. So these ADCs have good resolution. I can tell you right away where all our noise comes from. It comes from the nonlinear amplification. All the noise power. I mean, when you look at the curves we get. So there are several noise curves that I'm not showing you, or associated with these non-idealities that we see here. Maybe I'm sorry. I can show them because they're in my computer if you want to see them. But associated with all these non-alleles, we have noise curves. Right. And by far, the dominating curve is a curve of the amplifier itself. And so, really, for us, if we want to get better SNR, wider dynamic range, what it means is we need to work on the amplifier, not so much on the rest. Most of our noise is input noise that occurs at the amplification stage. It's input noise. So I see many hands, so I don't...
When you undersampled the wideband frequency signals using a frequency less than the Nyquist frequency, does it result in any aliasing in the spectral domain?
Yeah, if we don't have sparsity, but if we have sparsity, it doesn't really matter, right? What it's going to do is going to try to find the best compressed version of the object. And maybe that's good, maybe that's not good. It depends on the complexity of the signal. If the signal is sparse enough, that would be very good. If it's not sparse, it will not be good. Right? So to go back to this, if the input signal is this, I'm going to be terrible. If it's this, I'm going to be fine. Yeah.
I'd like to ask about your experience with the clock jitter. That's something which makes me feel a little bit worried because there is always this brick wall which you have to hit finally when you sample it with real high frequencies. But actually, isn't something like a clock jitter gives you uncertainty of the moment of sampling?
Yes, of course.
Isn't it a noise? Can you treat it as a noise?
Of course it's a noise.
But so then.
But it's a frequency-dependent noise. That is, the higher the frequency, the worse it is.
Okay, but
Right, because the error you get by clock jitter is, you think that you're sampling at t plus delta t. Right. So you think that you're believing that you're sampling at t, but in fact you're sampling at t plus delta t. Right. And so if you have a sinusoid that you're sampling, you can treat clock jitter thinking that you're sampling here when you're actually sampling here. You're going to make an error, and the error is essentially going to be frequency times delta t. So you can treat clock jitter, at least a part of the clock jitter that you cannot model, that you cannot predict, as additive noise. The thing is that it's frequency dependent. And as you're going higher and higher frequency, this noise is not following the thermal noise curve. It's at 6 dB instead of 3 dB. And that's what limits ADCs at the moment. That's the reason we cannot sample at a high rate. For two reasons. Number one is we lose enormous resolution when the sampling rate increases because of clock jitter. And now you have on this Walden curve, I don't know if you know it, you have the 6 dB line, which essentially corresponds to noise due to clock jitter. And then you have a brick wall, which is that capacitors cannot charge and discharge. They need settling times. And the speed is so fast that you cannot settle anymore. But there's a 6 dB line on the Walden curve, which is dominating in a wide range, which comes from this clock jitter, and of course we have to deal with this too. But we're sampling at a low rate.
yeah, although the resolution. I mean, if you have non-uniform sampler, but of course you sample it non-uniformly, but shouldn't be. I met this problem. The resolution of where the sample can happen. I found it should be.
Of course, it has to be controlled at the Nyquist precision, absolutely. Exactly. But I have a lot of time to kind of do my resetting or my electronics, because what we're doing is we take a uniform. The way the non-uniform sampler works is we take a uniform grid way below Nyquist, and then we jitter it. So there's a long time lag between consecutive samples. It's not that we have to make. It's not really random what we do, so that there is a bit of spacing. Of course, it's random in the sense that around each subsample point we jitter at random, but in between we have long time lags, and that's what makes it accurate.
The fact that you generate the random sequence of plus and minus ones in a very high frequency does not introduce a problem similar to that.
Yeah, of course, it does. It does. I mean, I cannot. It's what I just said. the system is not going to do this. It's going to do something else. But as long as I know what it's doing, I'm fine. As long as it's not shutting off high frequencies, I'm fine. But I need to know this guy. It doesn't have to be plus minus once, but I need to know it to within accuracy. But do you think that the sampler does this? Absolutely. The mixer does this? Absolutely not. It overshoots, undershoots, transitions a bit before, transitions a bit after. But we have to calibrate. We have to understand what it does. And that's where, I mean, the poor grad students spend an enormous amount of time on this. It's challenging.
Maybe one more question. Do you want to take your pick?
You showed some results, the recovery results for the two pulses, two modulated in frequency pulses, and you mentioned that the dictionary is not an orthobasis.
No.
It's
actually massively overcomplete.
Was L1 synthesis or analysis?
We do analysis plus reweighting.
Analysis.
That's what for us gives the best results. You can see that they follow very well.
Well, I imagine we'll be happy to take a few more questions in person afterward.
Sure.
Anyway, let me point out that Manuel's taken his spring break to come and give us his 10 hours of lectures of extremely high quality. It must have been a huge amount of work. So could we just thank him once more for this?